We are now starting chapter 7 about Laplace transforms. So transform is just another name for a function. The difference is that in functions we map a set of numbers to a set of numbers, but in transforms we map functions to functions. Actually, you might have dealt with some transform, or you have calculated some transform before. For example, if you have a function sine x and you differentiate, apply this differential, we call it the differential operator, and it gives you cosine x. So see, we had a function sine x, and it got changed to cosine x. So this is similarly the integral transform, something like this. Cosine, if I have cosine x here, this will be sine x. So now we look at this Laplace transform. The reason we are studying them here is because they are very useful or easy to solve. It makes the differential equation easier to solve, but it deals only, or it can solve only the linear differential equations with constant coefficients, not with the variable coefficients. Okay, let's start with the definition. So the definition says that the Laplace transform of a function little f of t defined on, so that this is the domain of t. So it means t is greater than or equal to 0. So the transform is given by big F of s, and it is this integral from 0 to infinity f of t e to the minus st. So previously, when you were doing integration in calculus 2, you would have an f of t here, and then you would have dt, and you can have 0 to infinity or any other limits. But here now, this is the difference, that this extra function is being there, and this is because of this is a Laplace transform. Although it is an integral transform, but so that's what differentiates it from other transforms. Now note here, when we have the function little f of t, the transform name will be big F of s. So that is another difference in these Laplace transform from what you have studied before. That previously, if my function is in t, my transform will be in t. My integral will still be a function of t. So for example, here we have a function of x, we get back a function of x. And same thing here, function of x, get back a function of x. But in here we have function of s at t, but we end up getting into the s. So we have the function of s. So we call this the t domain, and then the domain of f of s is called the s domain. S domain and t domain. So t domain is 0 to infinity, and s domain depends on a function, but on the the final answer. But just keep in mind that it should be all the values of s for which the integral in 1 exists. So for the value for which this integral exists. So and there is another notation for the Laplace transform. So in place of this f of s, we can use this one. It's scripted as L, and then we put braces, and inside here we put f. Sometimes we can put s like this here. So that is another notation. Now if you don't want to use this notation, it's hard for you to write or whatever, for whatever reason, it's okay. You can use big F of s, or if you have your function is g of t, then the transform will be g of s. If the function is y of t, then or y of x, or sometimes x, sometimes t, then this will be y of s. So whatever the function name, the uppercase is the name we use for the transform, Laplace transform. So the domain of f of s is all the values of s for which the integral in one exists. And note here that this integral is improper integral, and from calculus we learned that we can write the improper integral like this and do our usual process to evaluate it. So let's look at some examples. So the first example is determine the Laplace transform of f of t is equal to 1. Now I have done it here for you, but I am going to show you quickly here. So we want to find L of 1, which means our function f of t is 1 and we want to find f of s. By definition, f of s is equal to, remember, integral from 0 to infinity f of t times e to the minus st dt. So that in our case, because our f of s is 1, f of t is 1, so f of s will be equal to integral from 0 to infinity 1 into e to the minus st dt. Well, so I change it to the limit n goes to infinity 0 to n e to the minus st dt. Now if you can do it directly, integration, you do it directly, but if you want to use the u substitution here, you can do that. So I will do it directly. So it will give me minus 1 over s times e to the negative st. And so now I plug in the integration limits. Negative 1 over s. So integration limits, I get e to the negative sn minus e to the negative s times 0, or e to the 0. Okay, s has, the limit is not on s, this limit, so we can move this 1 over s in front. So negative 1 over s in the front, and I can take this limit now inside the bracket. So I bracket limit n goes to infinity e to the minus sn minus 1. Well, limit goes over here as well, but limit of a constant is just the constant. So, but what is this limit? So we are going to have to look at a function of this kind, or some number negative 5x. So if you recall, the graph of this function goes like this. So it is going to 0. So that quantity is 0. So I have negative 1 over s times 0 minus 1, which will give me 1 over s. Therefore, the Laplace transform of 1 is 1 over s. And the domain is s is greater than 0. Okay. Next example, compute the Laplace transform of e to the at. Again, I have done it here, but I am going to quickly show you. So we want to find L of the Laplace transform of e to the at. So remember, like we did before, this will be 0 to infinity. F of t is e to the at times e to the minus st dt. Okay, now we can change it to the limit like this, and we can put them together, the powers add, so we get at minus st. I would suggest that you write st plus negative st plus at, and the reason is, now we can take out a t common. So when we have s of t minus a of t, a times t, so we will take the t out, but also we will have the negative sign out as well. So negative I will put in front, t I will put at the end. So inside we are left with s minus a. And there is a reason for doing that, because eventually we will arrive at something like e to the negative s minus a times n, and limit as n goes to infinity. So in this form, written in this form with the negative sign outside, it clearly shows that if s is greater than a, which means this quantity is positive, then the limit goes to 0. But if I have it written like this, so then e to the n limit as n goes to infinity, it looks like it is going to infinity. But then it's, later on we can see here, it will go to infinity if s is less than a, or maybe less than or equal to a. So we have to be careful about that. So that's why we am putting the negative sign outside. Okay, so I have now limit n goes to infinity, 0 to n, e to the minus s minus a t dt, like before, just like what I just did. So the integral will be negative 1 over s minus a times e to the negative s minus a t, and then limits from 0 to n, and then I plug in the limits, and then take the limit as n goes to infinity. I can pull this one out in front and take the limit inside the like before, this quantity is 0, so we have negative 1 over s minus a minus 1, so you get 1 over s minus a. So this means that the Laplace transform of e to the at is s minus a. So what does that mean? Okay, previously remember we did that Laplace transform of 1 is, let me rewrite, 1 over s. Now we have Laplace transform of e to the at is 1 over s minus a. S has to be greater than a. So with these known, what you can do, how you can use them later. So for example, if you have to find the Laplace transform of, I think we will wait for that example anyhow. So let's look at next example, which is actually very, very long. I have done it for you. You will not be asked to do it in exam or in even, I think not even in homework, I hope. Okay, so here we are trying to find the Laplace transform of sine bt. Okay, so there's a long work and some, of course, integration technique learned from Calc 2, and then limits, applying limits. So we end up getting this as our answer. This is the Laplace transform of sine bt. Now the Laplace transform of cosine bt is this, which following the same steps and that much amount of work you can calculate that. Okay, next thing we talk about is linearity of the transform. So a transform is linear if it does this, that if you have to take the transform of a sum of functions. So you have two functions, you add them, and now you take the Laplace transform. So you will get the same answer as if you first take the transform and then add the transforms. Okay, this also then this will hold for negative subtraction as well. And this says that the Laplace transforms preserve addition and subtraction of functions. The second part of it is about constant coefficient. So if a function is being multiplied by a number, then the Laplace transform of that function will be the number times the Laplace transform of the function. So this is same thing that with derivatives. If you have three I think I will take ln of x. So if you want to differentiate this, you just keep the 3 as it is and then differentiate the function. So same thing here. Okay, together these two property we call this the linearity property. So find the example 4, find the Laplace transform of the given function. So here now you are given a function which is sum or difference of bunch of functions, and you can see there are numbers in front. Oh, by the way, so how will you use the other one that we did, this one? How will you use that one? Well, if you see something like Laplace transform of, let's say, 5. So now that we have learned the linearity property, we can think of it as 5 times 1. So you can say this is the same thing as 5 times the Laplace transform of 1. The Laplace transform of 1 is 1 over s. So we'll get 5 over s as that. And s will be greater than 0. So here we have 11 plus 5 e to the 4t minus 6 sine 2t. So I have to find the Laplace transform of this. By using the linearity property, I can separate it. I wrote Laplace transform of 11 plus 5 times Laplace transform of e to the 4t minus 6 times Laplace transform of sine 2t. So 11, as I showed you earlier, so you can think of as 11 times Laplace transform of 1, which is 1 over s. So you get 11 over s plus 5 times the Laplace transform of e to the 4t. So which rule will you apply? The Laplace transform of e to the at. So remember it was 1 over s minus a. So here I will get 1 over s minus 4. Then minus 6 times. So for the sine bt, we had the Laplace transform was b over s square plus b square. So what is the b here? So sine of 2t means b is 2. So I have, so this 6 is actually the coefficient. So that just stays there, and Laplace transform is 2 over s square plus 4. And then just simplify, and this is final answer. And same thing over here. First is 6t. So 6 times Laplace transform of t. Well, we haven't done, I didn't show you the Laplace transform of t, but you should be able to find it. But here is a table. This is a shorter table. There is a detailed, with more example functions in there, a table of Laplace transform at the end of the book. I think it's the last page of the book. Okay, so here are some formal transforms given. So if I have t to the n, t to any power, this is how it goes. It is going to be, the Laplace transform will be n factorial. I hope you guys know this, n factorial. So we assume that n is an integer, positive integer. So it can have the value 1, 2, 3, 4, 5, 6, 7, 8, and so on. We also include 0, but that is kind of a separately we include it. So this is how the definition of the integral is, that n factorial is equal to n times n minus 1 times n minus 2 times n minus 3 times dot 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 until you get to 3, then 2, then 1, and then you stop. You don't go further, because if I go further, next will be 0, and no matter how far I go on the right, the answer is 0, because we are multiplying by 0. So we do not multiply by 0, we stop at 1. So this means if I have 3 factorial, that is going to be 3 times 2 times 1. If I have 5 factorial, that will be 5 times 4 times 3 times 2 times 1. And similarly 6 factorial will be 6 into 5 into 4 into 3 into 2 into 1. So every factorial stops at 1. So you start with the number whose factorial is given, and then go down, 1 down every time, and until 1. Okay, so if you have t square and you want Laplace transform of t square, it will be 2 factorial divided by t raised to 2 plus 1, so t cube. So 2 factorial is 2 into 1, which is 2. So it will be 2 over s cube. If you have t, then your n is 1. So Laplace transform of t will be 1 factorial, which is 1, divided by s to the 2, s square. So you get 1 over s square. Okay. So now also notice here, so first we have these single functions, but now here is a product of functions. So we can again do it the long way, but here formula is given, so we will just use it. So this formula will be actually, there would be more formulas coming in, so they will be provided to you in the for the exam. Okay, so let's look at a couple of more examples. Okay, first, we had to finish this one. So here, so 6t. So we just saw that the Laplace transform of t is 1 over s square. So when we come here, Laplace transform of t is 1 over x square. So 6 times 1 over s square, or can be 6 over s square, plus the next is e to the negative 3t. So remember we said if it's e to the at, then the Laplace transform will be 1 over s minus a. So if you have Laplace transform of e to the negative 3t, so a is negative 3, so it means it will be 1 over s minus negative 3 or s plus 3. So that is what I have here, plus. So next is cosine of 3t. So I just showed you here that the cosine, this is the Laplace transform of the cosine bt, or you can look in here. So cosine, so what is the b here? The b is this quantity, square root of 3 is the b. So it is s divided by s square plus b square. So square root of 3 is 3, square of square root 3 is 3. So that will be okay. Let's look at a couple more examples. So we have now this expression. Now notice here we are having product of function. So we just follow the formula. So what is this looking like this one? So this says when you have e to the at times t to the n. So e to the at times t to the n. So we need to know what is my n, what is the a. So in our case, in the second example, second term, our n is 2 and our a is 1 because there is no number in front of t. So that when I plug it in the formula, the Laplace transform of this guy will be n factorial, which means 2 factorial divided by s minus a. A is 1, so s minus 1 whole raised to the power 2 plus b square. Oh, sorry, I'm looking at the wrong formula. Okay, go back. So it is this one we are looking at. So 2 factorial divided by s minus a, s minus 1 raised to n plus 1. So it will be cube. So it will be 2 factorial, which is 2 times 1, divided by s minus 1 whole to the third. Now for this last term, so it is e to the 3t. It means a is 3 and b is square root of 5. So just plug it in the last formula in the table, and we end up getting something like this over here. So this is your final answer. Another example, similar type of things. So first term is 4t cube. So remember, for t cube, so 4 is just a scalar which will just sit there, and we will apply the formula number 3 here. Use this one to figure out our transform. So it says 9 times, no, it was 4, okay, 4 times, if we had 4t cube, so 4 just stays t cube, so the transform will be 3 factorial over s to the 4, not t, s to the 4, and then so 3 factorial over s to the 4. What is 3 factorial? 3 into 2 into 1, which is 6, and the 4 was already there, so you multiply them, 24 over t to the 4, s to the 4, sorry. And 9 sine 4t. So this is like 9 can be pulled out, and you are going to look at Laplace transform of sine 4t, which is b over s square plus b square. So what is your b? The b is 4. So I have b over s square plus b square. So but there is a 9 in front, so multiply it with the 4 and you get 36 over s square plus 16. And then similarly we can find the Laplace transform of that, but now I have to put them together. So I said therefore Laplace transform of g will be equal to 24 over s square s to the 4, sorry, 24 over s to the 4 plus 36, or is it minus 36? Okay, this term is minus 36 over s square plus 16 plus 5 over s minus 2 whole square plus 25. So this is how you do the transforms. Okay, now we'll look at section 7.3.